Well, good day, everyone, and welcome to another session of this a year-long series, which we are organizing from the IEEE Electron Device Society Delhi chapter, New Delhi, India, along with the Deen Upadhyaya College, University of Delhi, under the Department of Biotechnology's Star College program. Today, we have with us a well-known personality in Electron Device Society, T.H. Ning, who has been a former IBM Fellow, and he'll be talking to us on the topic Symmetric Lateral Bipolar Transistor on Silicon-on-Insulator, SOI, a Shockley Transistor without Kirk effect. He received his PhD degree in physics from the University of Illinois in 1971, and he began working as a staff member at IBM Thomson J. Watson Research Center, New York in 1973, until his retirement as an IBM Fellow in 2016. He has made contributions to silicon bipolar, CMOS, and DRAM technologies, for which he has been recognized with numerous awards, including the Electrochemical Society 2007 Gordon Moore Medal, the 1991 IEEE Jack A. Morton Award, and the 1989 IEEE Electron Device Society J.J. Evers Award. He's a member of the U.S. National Academy of Engineering and a fellow of the IEEE and of the American Physical Society. With these words, I now invite Professor Ning to kindly share his screen to deliver his talk.
Thank you, Professor. Thank you for the introduction. Now, can you see my slide, or do I need to click something?
No, you have to share the screen again, sir. You have to click on the share screen option.
Okay. And
then there will be a dialog box. Yeah, it's coming up. Yes, maybe you can put it in the slideshow mode from the beginning.
Okay. Can you see the slide now?
You have to click on the slideshow, resume slideshow option, sir. There is a resume slideshow option. Yeah, slideshow. Resume slideshow from the beginning.
Yeah, I click it from the beginning.
Yes. Just click it. You have to, there is a resume slideshow option on the right-hand side. Yes.
Okay. Okay.
Yes. Yes, perfect.
Can you see now?
Yeah, perfect, sir.
Okay. Good evening. Good morning, in case somebody is from the East Coast of the United States. Thank you very much for inviting me to share my thoughts on the bipolar transistor. I've been working on bipolar transistor since 1977. And I must say that all along, we make progress, and most people just familiar with the vertical bipolar transistor, the hetero bipolar transistor, or silicon germanium bipolar transistor, and they're all vertical transistors. And one of the problem of the vertical transistor that we're familiar with is that as you try to turn on the transistor and let more and more current running through it, try to drive the transistor faster and faster. At some point, if you increase the current further, the transistor actually becomes slower. And it is due to a well-known effect called Kirk effect. And what it means is that for the familiar transistor, you should not run it at higher current than allowed by Kirk effect, which means that its speed is limited. And today I'd like to share with you, not that novel actually. Somebody published a paper on it before I stumbled onto it. It's a symmetric lateral bipolar transistor on SOI. And it is a Shockley-like bipolar transistor that has zero Kirk effect. The outline of my talk is I just briefly talk about the Shockley bipolar transistor structure, and then talk about the vertical bipolar transistor and how Kirk effect limit its speed. And then I introduce the symmetrical lateral bipolar transistor on SOI. And the absence of Kirk effect actually enables some unique properties of bipolar transistor for the first time in the history of bipolar transistor. And what it means, in my opinion, is that it provides opportunity and invite us to kind of revisit and rethink bipolar. Of course, all in the context of the symmetrical lateral bipolar transistor structure. Shockley invented the sandwich-like bipolar structure in 1948. Okay, the patent filed in 1948. And if you look at it, even during the filing and the band diagram, when you operate the transistor, it's almost just like the transistor we're familiar with, we learn about in school and in reality all these years. So the foundation was laid out by Shockley back then when he first proposed the sandwich-like bipolar transistor structure. I've been working in IBM since 1973, and in 1977, my assignment was switched to bipolar transistor. At that time, the most advanced bipolar transistor produced in the world, including in IBM, was like shown in this slide. The left-hand side one here is the earlier structure. The emitter area is actually the active device area. One look at it, you see that a bipolar transistor, the active device area is very tiny compared with all the area taken up by the transistor. Why it take up so much area? Because the isolation. Okay, you need this very deep P pocket to isolate the transistor from its neighbor. A little bit later, okay, all the effort is to reduce the parasitic. They introduce a recessed field oxide. The way you do it is that you etch down the silicon halfway and then you grow the oxide. Because when you grow silicon dioxide, you use up about 50% of silicon. So on 1 micron silicon, you can grow 2 micron of oxide. So the P pocket become a lot smaller and a lot less parasitic. And as a result, the transistor is significantly smaller. But still, the active area is tiny compared with the rest of the device area. The modern bipolar transistor, many of you are probably familiar with and hear about, particularly in research paper and in production, is as shown here. The left-hand side, this SEM is actual SEM of a silicon germanium bipolar transistor. The right-hand side diagram here shows the schematic, what it looks like. It has polysilicon emitter and really ultra-thin base. This polysilicon emitter enables the achievement of the ultra-thin base. And the emitter is self-aligned to the base contact by this lateral sidewall oxide. And it has a pedestal collector. This is the collector dopant concentration. You can be introduced very easily by ion implantation during the emitter opening. And because the design of a bipolar transistor to optimize it is depending on the collector dopant concentration. So by having this emitter window open, you can introduce the correct or the desired collector dopant concentration to optimize the transistor design. And of course, you have deep trench isolation. And this shows the typical vertical profile of advanced bipolar transistor. You can see that this is the polysilicon layer, the so-called polysilicon emitter. Of course, the doping from the polysilicon does go into single crystal a little bit, but it's very little. You just need enough thermal activation to activate the polysilicon emitter, and that's it. As a result, the emitter junction is ultra shallow. And this ultra shallow emitter junction enables you to have a very well-controlled ultra thin base. And this is the collector dopant concentration, collector. And it is obvious from here that the collector dopant concentration is much smaller than the base dopant concentration. Typically, the collector is 10 to 100 times lower concentration than the base. This is important, as you see in a minute. Okay. When you operate the bipolar transistor, whether it's lateral, vertical, the principle is the same. You forward bias the emitter base junction. Electrons are injected from the emitter into the base, and they pass through the base and reach the collector and give rise to a collector current. But the holes are injected from the base backward into the emitter. And this whole current from the base is the base current. Now, let's look at it a little bit more, the kind of unintended second order effect. When you forward bias the emitter base to inject electron from the emitter into the base, the electron flows into the base, through the base, and then arrive at the collector. Now let's take a look at the emitter base junction space charge region, this region here. The amount of space, and in this case, the diagram here is for zero emitter base bias. Basically, the emitter base dial is at thermal equilibrium. And the charge, space charge on the collector side has to be the same as the space charge on the base side. This from Gauss' law. Since the collector is more lightly doped, the space charge layer width on the collector side is wider than the space charge layer width in the base side. Now, when you forward bias the emitter base dial, electrons come in. These mobile electrons coming from the emitter into the base and through the collector, they contribute to the space charge carrier density, which means that now suddenly you have less space charge here, because the positive charge minus the negative charge coming from electron, okay? But the space charge here on the base side become higher. You have a negative space charge plus the mobile electron. As a result, the space charge layer on the collector side become wider. Now you can imagine that as you increase the emitter base dial, more electrons coming in, and this on the collector side, the space charge layer basically push all the way towards the subcollector, as shown here by simulation done years ago by Poon and Gamo. This is the transistor they simulated. As you can see that the electric field in the junction at low current is located right at the base collector junction. This is the peak electric field. As you increase the collector current, this space, the maximum field point, move towards the collector until it kind of reaches the subcollector. Basically, for vertical bipolar transistor, once you operate the transistor by forward biasing the emitter base dial, the base start to widen towards the collector. The only way you can stop it is by the subcollector. If the subcollector is not there, you just keep pushing to the right. One of the principles of operation of a bipolar transistor is that in a quasi-neutral region where you have no high electric field running, should be charge neutral, which means that if you have more electron there, you got to have more holes there to balance it, which is delta N equal delta P. And this is the delta N extra electron due to operation of the transistor. You can see that as you have operate the transistor and higher collector current, there's a buildup of electrons in the base as well as in the collector. Now in the collector, it's fine. It is anti-region. You just have more electron than the collector dopant concentration. You can see that. But if holes in p-type region type collector. As you remember, when you learn about PN diode, when you forward bias it, you turn it on very fast. But when you turn it off, it doesn't turn off fast because the minority carrier in the forward bias diode has to all be drained out or recombined before the diode is really turned off. So it is this extra holes in the anti-region that slow down the transistor when you try to switch it off. So if you look at a bipolar transistor, you try to switch it, there are several major delay components. What I plot here is the log of the gate delay and log of the collector current. This is the device and wire capacitance component. The higher the capacitance, the higher the line would go towards the right. But they always decrease as you increase the current because CV over I, okay? You just increase the current, the delay component will come down. And there's a kind of base transit time or base width component, this horizontal line to first order is flat. So a Y base, the delay component is higher. A very thin base, the delay component is smaller. But there's also this delay component called diffusion capacitance. One of the things about switching of a diode is that all those electrons and holes moving around, they contribute to a delay capacitance component called diffusion capacitance. The more electron holes flowing around in the device, the higher is the diffusion capacitance of the device. So as you saw in the last slide, as you increase the current of a transistor, there are a lot more minority carriers stored in the collector, in the vertical transistor. And this delay, diffusion component causes a delay. And as you can see, all vertical bipolar transistor, as you increase the current, the delay becomes smaller and smaller until you reach some point where the diffusion capacitance kind of take over. So the more current you pump into the transistor, actually the transistor runs slower. You do not want to operate a transistor at a current that actually make the transistor run slower. Okay, which means that you always want to operate the transistor to the left side of this valley. Because there's no point operating it on the right-hand side. You actually burn more power and yet transistor runs slower. And this is due to Kirk effect. So Kirk effect determines the maximum speed of a vertical bipolar transistor. And you actually see this in all the publications. Typically, people would plot the FT or gate delay, 1 over gate delay as a function of the collector current. you typically see that as you increase the current, the FT becomes higher and higher and higher, and then it peaks. If you pump more current through the transistor, not that the transistor cannot carry more current. It's just that those additional current actually cause the transistor to become slower, and it drops very, very rapidly, as you can see in all the plots. The same thing applies when you take a logic gate and plot the gate delay. In this case, it's just that the gate delay becomes smaller as you increase the current. And then at some point, Kirk effect kicks in. You try to pump more current through the circuit, it actually becomes slower and slower. And what is plotted here is everything the same, except they use two different size transistor emitter area. One is about 5.2 times larger area than the other one. You can see that the minimum delay shifts to the right by about a factor of 5.2 when you plot things on as a function of current. So actually, using a larger area device, even though at low current, you find that, oh, larger device area, you got more capacitance. But actually, when you want to maximum speed, the larger area device can reach a higher speed. And the higher speed, again, is determined by Kirk effect, okay? Not by the base width, because these two transistors have the same base width. Now, Kirk effect in a bipolar transistor is a function of the collector dopant concentration. That's why I showed you earlier that the pedestal collector is very nice feature that allows you to tailor the collector dopant concentration directly underneath the emitter to tailor the collector dopant concentration. So you can actually push out Kirk effect by increasing the collector dopant concentration. In this case, this collector dopant concentration is increased by a factor of 2. You can see that the peak can occur at twice as high current. One thing you have been observed from all the publication, and here's just one example, that the peak speed of peak cutoff frequency of a vertical bipolar transistor is determined by a current density, which is approximately a little bit less than the maximum collector dopant concentration times the saturation velocity. What it again kind of demonstrates that you should not operate a vertical bipolar transistor at a current where the electron coming from the emitter, the density of electron coming from the emitter is higher than the collector dopant concentration, because the collector simply cannot carry those currents. So now we understand what limit the speed or performance of a vertical bipolar transistor. It doesn't matter you have silicon germanium. It does not matter whether you have the junction. It is the collector doping profile that determines the maximum speed of a vertical bipolar transistor. Here, let's take a look at a symmetric lateral bipolar transistor on SOI. For those who are familiar with CMOS, I'm quite sure you're all familiar with CMOS. Think of it as a SOI CMOS transistor with 0 gate oxide. Okay, think of it in that way. And then you can understand how this whole thing works. It has no Kirk effect because the collector dopant concentration is the same as the emitter concentration. There's no lightly doped collector. You can think of it, you have only the subcollector, and the subcollector is the same as the emitter. Or you can think of it as you have only the collector okay, and the collector is the same as the emitter. By symmetry, you can usually see that whether you switch whether you call the left-hand side as the emitter or the right-hand side as the emitter, it doesn't really matter. What it means is that the transistor can be switched by switching the emitter base dial or by switching the collector base dial. Just like in a CMOS transistor is symmetric, whether you switch source or switch drain. And without Kirk effect, the transistor can be operated at much higher current density than a vertical bipolar transistor without speed degradation. Not that you cannot pump more current into it, but vertical transistor, you pump more current into it, you actually slow down the transistor. But here you would not. And this is some measure data and model. You can see that why lateral bipolar transistor, it kind of lay out like a CMOS transistor. Yeah. Why it has a larger than a MOSFET drive current, basically per transistor width. For those who are familiar with MOSFET, typically a MOSFET, the maximum current is approximately 1 milliamp per micron of gate width. That's it. You can look back and look at literature for all the generations is approximately 1 milliamp per micron gate width. But the measured data here shows that a lateral bipolar transistor, you can measure about 5 milliamp per micron for silicon thickness of about 60 nanometer. Since the current is proportional to silicon thickness, the thicker the silicon you use, the more current per width you can achieve. Okay. And to understand why it has such a higher current than MOSFET is very simple, because you just take a look at, assuming you have a base doping concentration of 10 to 19, 100 nanometer or silicon layer thickness, you got a whole density of about 1E14 per unit area. And CMOS, a MOSFET, typically when you turn on the MOSFET, the inversion layer density is about 1E13. So inherently, you can easily have 10 times as many carriers in the active device channel, for SOI bipolar than for MOSFET. And I already talked about that. The emitter-collector symmetry means that you can switch the emitter base dial, or you can switch the collector base dial. And also, there's no penalty in operating transistor in the saturation region. You may recall, as we learn about vertical bipolar transistor, you say try to avoid operating a transistor in the saturation region, because this region is where the collector base dial is forward biased. A symmetrical transistor has no problem because emitter base switching, collector base switching is the same. One other thing to avoid saturation for operating a bipolar transistor, you can easily understand it by just looking at the dial. You have a transistor here, you have a resistor here, you have a collector bias voltage, power supply voltage, VCC. The collector voltage is here, Vout is equal to VC. Okay. VC is equal to Vout minus VCC, V is equal to Vout equal to VCC minus this IR drop. So as you turn on the transistor more and more, the IR drop here become larger. It pushes Vout closer to the ground. So to avoid Vout going to saturation, what do the designers do? You increase VCC, you put it out high enough so that VCC minus the IR drop, leave V out always higher than V input. This is the standard way of avoiding a transistor going to saturation. You use a larger VCC. But if this transistor were a symmetrical lateral bipolar transistor, it's okay. Let it saturate. You can have actually VL all the way going to the ground. The transistor come back from saturation just like you switching a transistor from on to off. No performance degradation. What it means is that for the same bipolar circuit using conventional bipolar circuitry involving resistors, you can operate the bipolar circuit at a lower power supply voltage if the circuit is implemented in lateral bipolar transistor than the circuit operated in traditional vertical bipolar transistor, which means that the same circuit, everything is the same, it is lower power. And it can be integrated, PNP, NPN on the same chip, just like CMOS. And in fact, this is hardware. And this is the first hardware in our reported experiment about 10 years ago. You got NPN, PNP on the same chip, and they work, okay, as expected. Can it be scaled? We know that MOSFET can be scaled, CMOS scale. Of course, scaling always has a limit. And if you look at the scaling of a lateral bipolar transistor, one thing about it is that this N plus P Dayal physical boundary condition is fixed for a bipolar transistor, no matter how you bias it. There's a depletion layer width is extended into the base from both the emitter side and from the collector side. So the actually base width between these two dotted lines, WB, the base width, is equal to the emitter-collector separation minus the two depletion region width. And the calculation shows that depending on the base shift resistance you want, you can easily have emitter-collector separation of less than 20 nanometer, which gives you a physical base width of about 10 nanometer or a little bit smaller. So you can easily scale it down to 20 nanometer emitter collector separation of N plus separation. Now, if you look at bipolar circuits over the years, back in 1972, actually, there were a lot of excitement. And at that time, CMOS were at 5 volt or higher voltage. And CMOS were at 5 micron dimension or around there. I2L circuit was invented. And a lot of excitement. Why? Because I2L circuit or integrated injection logic circuit is by far the densest logic circuit in CMOS or in bipolar. It requires only one PNP transistor per gate for injecting current. And then for each fan out, you have an NPN transistor. And the NPN transistor is operated upside down. Basically, in a vertical bipolar transistor, the I2L circuit, the bottom N plus is used as the emitter of this transistor, and the collector is the output. So it will lay out in this very dense way, circuit-wise, operate in this way. And experimentally, back in 1980 or so, the experiment shows that I2L in vertical circuit can operate at a little bit less than 100 picosecond. At that time, it was very fast, much faster than CMOS. But the problem is that this 100 picosecond or so doesn't come down very much as we scale it. The main problem is that because the transistor operated upside down, you switch the collector base dial, and that is very slow, as we saw, just like Kirk effect limiting the speed of a transistor. So they're not compatible with CMOS, not competitive CMOS. Industry lost interest in that. However, if you look at it again today with lateral bipolar transistor, the simulation shows that you can actually get to sub 10 picosecond delay. And the device has very small capacitance, very small device area, and very small power delay product. And similarly with lateral bipolar transistor, it's time to kind of revisit complementary bipolar. Back in 1976, people actually invented a bipolar analog of CMOS. Okay, this is the two-way NAND circuit. But to operate this circuit, you require the collector-based diode switching. And of course, there's no collector-based diode switching bipolar circuit that is fast. So there was never built. This circuit was never built, never even simulated. No interest, because when you look at it, you know it's theoretically it can be done, but it's awfully slow. But symmetric lateral bipolar transistor is perfect. It's ideal for implementing this CMOS analog complementary bipolar circuit. In fact, there's a recent paper just published less than 12 months ago. For those who are interested, take a look at this paper. It did simulation compared with CMOS and showed that it has all the attributes like CMOS, except that it is faster. The same circuit can be operated at ultra low power mode by running at low power supply voltage or at very, very high speed when you use a higher power supply voltage to operate this circuit. And actually, this inverter demonstrates the work. We measured it. All right. And the simulation shows that if you extrapolate to a smaller dimension, you can actually get to sub-picosecond delay as expected by other simulation. So it shows that complementary bipolar as a circuit, it does work. In my opinion, the I-square logic circuit is simpler, involve fewer transistors, could be even more interesting. Now, one interesting about bipolar circuits, complementary bipolar circuits, or I-square circuit using this lateral bipolar transistor is that the same circuit can be used in either high performance mode or ultra low power mode. Now, with that, you can think about designing a microprocessor chip, a multi-core chip. Nowadays, all the microprocessor chip from Intel, AMD, you buy or in your computer, there are many, many cores, okay? At least a few, because they don't make single core chip anymore. It takes up too much area for bonding and all that. You can have most of the core running at base speed in the ultra low power mode. You can imagine one or couple core running at higher speed. And then you have one or two core running at ultra high speed as accelerator. If you take a CMOS chip, okay, or your microprocessor, you say you run it in turbo mode, what does it mean? They tell you, you shut down a couple core and put all the power into this one core, and you speed it up by how much? 20%, 30%, that's about it. But you can imagine with this new bipolar technology, you can have a multi-core chip, okay, that have low power, ultra low power, accelerator, all integrated on the same chip. Or if you like, you can have just each one of the core, you run them at low power mode, speed it up, and higher power mode. Okay. those are opportunity for system design innovations. So to summarize, in my opinion, this SOI symmetric lateral bipolar on SOI is an intriguingly interesting technology. It has no Kirk effect, so you can operate much higher current, and it has much smaller device capacitance. So higher currents, smaller capacitance, you can reach much higher speed. And I think more interesting is opportunity to revisit bipolar. With NPN, PNP integration, you can imagine all kinds of innovation, take advantage of CMOS infrastructure. And higher current, you can think about using it as the drive current for the universal memory, like MRAM or phase change memory, which need a lot of current. Or you can have this system design innovation. And the low capacitance, high current actually can lead you to terahertz without having exotic device structures. And finally, I have a list of the references for those who are interested in looking at a little bit more. That's it. Thank you very much for your attention.
Thank you very much, Professor Ning, for such an insightful talk, which covers nearly 50 years of your research and teaching experience, I can say. Yeah, thank you very much. So there is one question which I can see has been shared. How does the device structure optimization can further reduce the Kirk effect as well as diffusion capacitance in a vertical structure of a transistor?
Well, if you say, no, I'm stuck with vertical bipolar transistor structure. Theoretically, okay, one device design concept is that you use heavily doped. Basically, if you go back to, let me see, I can show you this device structure. Okay, conceptually, people are talking about, why don't I have this subcollector, okay, butting right up to the base width? Basically, I skip the lightly doped collector. So you got an almost symmetrical device structure. What's the problem with using such heavily doped collector? Basically, you have a collector as heavily doped as the subcollector. What's the problem with it? The problem is that you can see from here, if you move the subcollector all the way up to touching this N+, the P+, or the P region, P+, you got huge base collector diode capacitance. It's just that the vertical bipolar transistor, by its very nature, the way it's implemented, okay, the collector base area is a lot larger, much larger than the emitter base area. So that's why people don't do it. That's why people do not move the subcollector all the way up to touch the base. I'm not answering the question. In my opinion, and conceptually can be done, but you do not get really much benefit from that kind of design.
Okay.
But the lateral transistor is inherent, it's built in.
Okay. I'll take up the next question. In an upgrading world of quantum electronics, how do you see the future of bipolar junction transistors?
Quantum, what do you mean by quantum electronics? Quantum computer and all that. I look at it in the following way. Quantum computing is being worked on now, and it is in a small scale, it is here. In fact, today, for anybody, you can sign up to have, through the cloud, have an account to sign up to use IBM's quantum computer, which are available. I do not know what the terms are. It's certainly available for research and certainly available for industrial use. You can look into that. But the given quantum computer, if you look at what is being talked about, is that only that core, that a couple core is quantum computing. Everything else is room temperature electronics. You can put some control electronics down to low temperature for next to the quantum computer, but once you go away from it, it is other electronics. It's kind of like today, you look at a microprocessor chip. It has a lot more transistors you ever need for the whole computer or for your whole iPhone. And yet the iPhone has a lot more circuitry than the core. So you have other things. So I am seeing that CMOS as a room temperature logic, memory and logic, or bipolar as a logic and memory is not going to be replaced by quantum computing. Quantum computing is simply kind of like an accelerator, special purpose core to meet your need.
Okay, sir. Well, we have Professor Giorgio Beccarani and Professor Rudan also as the panelist. I request Professor Giorgio to kindly unmute and give his comment or any questions which is related. Yeah, over to you, sir.
Thank you, Professor Saxena. Hi, Tech. I find your presentation extremely stimulating, and I myself have understood the Kirk effect better than before now. But I would like to ask you a question. You mentioned a typical silicon thickness of 60 nanometer in order to support that high current of 5 milliamps. It seems to me that this kind of thickness is not very compatible with today's CMOS fully depleted SOI technology. And I am wondering whether you think of chips which should only be based on bipolar technology separated from those made in CMOS, or if you think to combine the two technologies in one single chip.
Okay. Thanks, Giorgio. Nice to meet you again on via video. Well, this silicon thickness was used. We used 60 nanometer because at the time we do the experiment, IBM was using SOI,
partially depleted.
CMOS. At that thickness, we simply take the wafer and take the mask set and run with it. Okay, here's the physics, right? The thicker the silicon, the more current you can get, and is proportional. Actually, if you make using a thinner silicon, which means that the base resistance, which is vertically from the P plus polysilicon down to the box, the thickness is the base resistance, right? Thinner silicon means smaller base resistance. In fact, simulation suggests that smaller base resistance, the bipolar transistor can give you higher F max. Simulation is not here in the reference. You can see that you can get terahertz F max easily. So whether we use thin silicon, thick silicon, I think it's totally dependent on the application. The point I want to make is at this point is that let's understand the possibility and capability. How do we combine things is really depending on the application and the manufacturer, the foundry companies who are willing to say, okay, I'm going to put out a standard offering of 20 nanometer instead of 16 nanometer. Because until the foundry people do not offer that, okay, you can do all the simulation you want. Of course, in university lab, in industrial lab, you can do some experiment. In my opinion, what is needed to drive this is for university, industrial labs, okay, to do simulation, or because the physics is fairly well understood here. The simulated result is quite believable because this is not like something you do not know what's going on. So people say garbage in, garbage out. I don't believe your simulation. But bipolar, silicon, you can believe in the simulation, okay? And use those simulation results to suggest that, okay, I can do this, I can do that. And then work with industry, say, okay, give me the most challenging application. What is it you don't like with CMOS you have that you like? And let me take a look at this thing. And hopefully the simulation suggests, come back and say, haha, guess what? You can get much better result. You can beat your competition if you have this technology or this combination technology. And show it by simulation and use those results to drive the necessary investment needed, in my opinion. Because until that happens, it's not going to happen. As you can see in IBM, I did the experiment because we have the SOI CMOS technology there. When we did the experiment, when we published it 10 years ago or 11 years ago, we actually just literally used the CMOS mask set, used the CMOS SOI wafer, and we just come up with a process to make zero-gate oxide type of experiment. Aha, boom, we run number one, it come out working. Not unexpected, but we were surprised it worked. And from then on, we did a couple more experiments to understand things a little bit more. So I think once there's some simulation to drive some curiosity, you can use terahertz electronics as an example. Now people talk about 6G. What is 6G? Okay, what's the technology to support 6G? Can today's CMOS support 6G? I do not know. I have not looked into it. But I know that I've done simulations showing that if you use a thinner silicon, 20 nanometer, maybe even 10, you can get 1 terahertz or higher Fmax. The question is, who cares? So I do not know if anybody cares. I keep hearing that they want terahertz, but who has terahertz? Okay, and I'm saying there's a possibility. This can be terahertz, and that is what's needed. That's my thought.
Okay, thank you.
Thank you. Thank you very much, Professor Ning, as well as Giorgio, for your point intervention. And this brings to an end of a wonderful session for today. And on behalf of IEEE Electron Device Society Delhi chapter, as well as the ad hoc committee, which has been created by IEEE EDS, Board of Governors, for the celebration of the 75th anniversary of Transistor, I would like to thank Professor Ning and to all the attendees for being there with us today. And I invite all of you for another interesting session scheduled for February 8th by Giorgio Micheli. Thank you very much, sir.
Thank you.
Thank you.
Thank you.
Bye-bye.
Thank you.